All right, so we're moving on to some of the other equations from this chapter. Namely, we're going to look at Charles' law and Boyle's law. So let's look at two more examples in this video. First, let's read the top question. Ignoring effects from temperature, what would the volume of a balloon be on Venus, where the atmospheric pressure is 90 atmospheres, if the balloon has a volume of 3 liters on Earth? And then a second follow-up question, what about on Mars, where the pressure is very tiny, it doesn't have an atmosphere, 0.006 atmospheres of pressure on Mars. All right, well, let's read through it one more time and write down our known information. So, ignoring effects from temperature, what would the volume of a balloon be? So we're actually asked for volume in this problem. That's going to be our final volume. The pressure on Venus is 90 atmospheres. Well, this is all starting on Earth. If the balloon has a volume of 3 liters on Earth, so its initial volume is 3 liters. And what's the pressure on Earth? How many atmospheres do we have? Just one. The initial pressure is not given, but it's inferred because we are on Earth, where the atmospheric pressure is 1 atmosphere. And then we're going to follow this up, what I'll call a V3 and P3 for Mars. What is going to be the volume on Mars? And the pressure on Mars we know to be 0.006 atmospheres. All right, well, we've written down our given information, and as promised, it should be pretty obvious what equation to use. We've been given volume and pressure, and we've been given volume and pressure in 3 pairs. Volume and pressure on Venus, volume and pressure on Mars, volume and pressure on Earth. Well, if we look at our equation sheet, there's only one equation that uses volume and pressure together. And the way I like to write that equation is P initial, V initial equals P final, V final. That the pressure times the volume needs to be a constant. So whatever it is at one place, when we combine those variables somewhere else or at some other point in time, it better combine into the same number. Pressure times volume always equals the same thing. And what are we solving for? We're solving for final volume. So to get that final volume by itself, let's divide by the final pressure. The final pressure cancels, and our equation is V final equals P initial, V initial over P final. So what's the volume of this balloon going to be on the different planets? Well, let's think about what to expect before we actually plug some numbers in. On Venus, the pressure goes up. We started at 1 atmosphere on Earth. We go up to 90 atmospheres of pressure on Venus. It's a whole lot, and it's pushing down on that balloon. That balloon's going to shrink. We should have a much smaller balloon. We should expect a smaller volume on Venus. Well, what about on Mars? On Mars, there's barely any atmosphere. It's hardly pushing at all. So we go from Earth, where there's a solid 1 atmosphere of pressure, and then we go to Mars, where it's barely pushing at all. Well, that balloon has the opportunity to expand. We should expect a much bigger volume on Mars. So let's see what we get. So first, let's do Venus. On Venus, V final is going to equal initial pressure, 1 atmosphere, initial volume, 3 liters, over final pressure, 90 atmospheres. I can see atmospheres canceling. That's our pressure units. We're left with simply volume units, liters. 3 divided by 90 is 0.033 liters. And indeed, our balloon shrunk. It once was 3 liters. It once was 3 liters of volume. It is now 0.03 liters of volume. It went down by a factor of almost 100, a factor of 90, it turns out. And then what about on Mars? On Mars, our final volume is going to be initial. Those are the same. 1 atmosphere, 3 liters. And we divide by our final pressure, which is 0.006 atmospheres on Mars. Again, the atmospheres cancel. The units turn out to be the same. We're going to end up with liters. And on Mars, this balloon expands to a massive size of 500 liters. I hope it's made of a very good material because that's probably going to pop. But the effect is very obvious. Whenever you have more pressure, you get less volume. Less pressure, more volume. Those things are inversely proportional. But these problems, as I said, they are fairly quick and easy. If you write down your known information, it's easy to recognize what equation to use. And once you've got the right equation, the algebra is generally one step to rearrange for whatever variable you're solving for. And then you simply need to plug in some numbers. So let's look at the other example on this page. Because Mars has very little atmosphere, its surface temperature varies wildly from day to night, reaching temperatures around 20 degrees Celsius during the day and falling to negative 100 degrees Celsius at night. If you blew up a balloon to a volume of 3 liters during the day, that is when the temperature is 20 degrees Celsius, what size would it be at night? So, looking back to this problem, let's write down the information we were given. We know that we're going to blow this balloon up during the day. So the initial temperature is 20 degrees Celsius. And that initial volume we blew it up to was 3 liters. We then wait till nighttime. The temperature plummets to negative 100 degrees Celsius. That's going to be our final temperature. What is the final volume? What size is our balloon? Well, what should we expect to happen? The temperature goes down, the volume should go down. We should expect this balloon to shrink whenever it gets cold outside. Let's see if that happens. So, what equation are we going to use? Well, we've got temperatures and volumes, a pair of temperature and volume, a pair of temperature and volume. Again, it's fairly obvious what equation to use. We use the equation that combines temperature and volume. So, T initial V initial over T initial equals V final over T final. And what do we want to solve for? We want to solve for V final. Right there. To get that, we need to multiply both sides by T final. Multiplying by T final cancels on that side. And our final equation is V final equals T final times V initial all over T initial. Now, I'm about to make a mistake here, so hopefully you will learn from my mistake. I'm going to walk right into it. Some of you might already be screaming, no, don't do it, because you might see what I'm doing wrong, but let's plug in some numbers. T final, negative 100 degrees Celsius. V initial, 3 liters. We divide by T initial, 20 degrees Celsius. Well, what's going to happen? I see degrees Celsius canceling with degrees Celsius. I've got 100, negative 100 divided by 20 is negative 5 times 3. I get negative 15 liters. Negative 15 liters, does that make sense? Negative volume, it doesn't make sense. We cannot have negative volume. As I threatened you guys with the snipe hunt of going to Walmart and looking for a negative liter water bottle, we just can't have this. What did I forget to do? I forgot to convert my temperatures to Kelvin. because we have ratios of temperatures popping up. T final over T initial. We cannot have negative values for temperature. However, they're quick and easy to convert. We add 273, so this should be 293 Kelvin. Our final temperature was negative 100 degrees Celsius, so our final temperature is 173 Kelvin. And let's try plugging in numbers again. Once more, one last time, V final should be T final, which is 173 Kelvin times 3 liters, divided by T initial, which was 293 Kelvin. Kelvin cancels, and V final ends up equaling 1.77 liters. 1.77 liters. That is our final answer. That one didn't make any sense. Negative volume doesn't make sense. Additionally, that number actually went up. We said we should expect that volume to go down. Well, disregarding the negative sign, that number also went up. That won't always happen. The negative sign is our big red flag. But indeed, our volume went down whenever the temperature went down. That is consistent with what we expected, and that is the actual correct answer to this problem. So hopefully seeing that mistake made will keep you all from making it. But please do not forget to convert your temperatures to Kelvin in this chapter. All right, we'll have one more set of examples, and that will conclude chapter 9.